and composing very large scale systems that involve all these different components. And I think indeed in the future there perhaps will be some general idea as to how we could go about these. So this is interesting because Donna gave a very good talk earlier on today, and in fact we have a Woods Hole vehicle that we bought from them. At the same time as buying the vehicle, we also acquired a person from Woods Hole, which was useful. He came with it. And in fact, we've just acquired another person from Woods Hole. Australia is a wonderful place to do offshore underwater stuff because it's always nice and sunny and warm, basically. So our focus in this is not necessarily deep work. Our vehicle it's untethered and goes down to about 700 meters. But in particular, actually doing the sort of autonomy components that our scientists are interested in. And most of the scientists that we're interested in are basically, what the scientists are interested in is getting long transects which are all accurately geo-registered and so on and so forth, in usually many different environments. So the problem we've been focusing on is actually generating SLAM solutions for problems like this. So this vehicle comes equipped with a multi-beam. We've got stereo imaging on it as well. We've also got Doppler and so on. But the task is really to get accurate navigation solutions for this. And we've worked now on my colleagues Stefan Williams and Oscar have worked pretty hard on generating solutions using the SLAM type algorithms for these sorts of things, because people want to then take that information, do automatic classification, do efficient surveys, and so on and so forth. And I'll talk a little bit about those when I've said something about the SLAM problem itself. So this is a pretty challenging application for SLAM. There's no decent features underwater on the average, certainly no lines and points and things like that. But nevertheless, there are techniques out there now, particularly these appearance-based techniques, that actually allow you to not use this as the map, but actually create a map just from the trajectory of vehicle locations. All right? And this is a very useful concept because it means that you can actually store all this information and then re-register the information once you've actually got an update from the map itself. And there's been some pretty good recent advances in this area, not just in our group, but John Leonard and other people, that you can now get exact constant time vehicle and covariance information out of algorithms that use this. And on typical missions, for example, we might gather 2 terabytes of map information. All right, so you're updating that as part of your map in SLAM. So this gives you an idea of the sort of thing that we're generating. This is, for us, a reasonably long transect, and I'll just go up to the first point that it updates. And in effect, what's happening as far as the SLAM problem is concerned is we're just creating a massive state vector. Every time we move, we're just augmenting the state vector and doing nothing with the map. Augmenting, 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 and so on. And we're essentially storing that information and waiting until the point where we come back and basically revisit one of the areas that we've seen before. At the point that you revisit that area, you can then back propagate and do marginalization over the states. Okay? And at that point, you can then update the map and use that to actually register what's going on. So if I show you how the re-registering works, we're using some fairly simple machine learning techniques to actually extract useful information from images. But you can see we're using stereo imaging, incidentally, to do the maps. So you can see the sort of associations that we're performing as you get the crossover, another association, and so on. But the big deal as far as the scientists are concerned is what they end up with at the end of the day. Oh, and I have to say from Matthew Johnson Robertson, one of Red's former students who's been working with us on exactly this problem. You can see this is his video. This is the sort of thing that the scientists get back. This is a completely geo-registered map, very detailed visual information of what's going on in the seabed, so they can basically see exactly how everything fits in, what's down there. It's full three-dimensional information from stereo. And in a second you'll see we also have now sub-algorithms which take that and actually apply interest operators that say, okay, you guys, you need to actually look in these areas for the things that you're interested in for this particular survey. They may be height differences. We also use entropy and other types of measures for finding different types of corals and sponges and so on. But this in the end is extremely valuable information for the scientists to actually generate new science information. And this is really what they want. So we've done a large number of dives now, and I'll show you that on the next overhead. In fact, they've just got back from the last one down in Tasmania here, doing 20 dives in 10 days, using that SLAM algorithm on each dive. So the SLAM algorithm, perhaps it's not as reliable as short baseline sonar yet, but it's getting there. We're pushing the technology to the point where scientists can reliably use a SLAM type guidance algorithm to get their information rather than having to deploy other technology. So we're operating it as part of, again, very similar to what was said earlier, we're living on the back of a very large science program. The large science program is all about the Marine Observatory, and what we're simply doing is providing the autonomy component for that and doing different experiments that the scientists can actually do, are actually interested in. And I have to say, again, echoing one of the earlier speakers, it's an extremely exciting place to work, because these guys really come up with, when they actually see some of the results you're generating and they come up with new science discoveries on the back of that, it's extremely exciting to do. So we've been doing a number of different ones. These are work that's actually been done out at Ningaloo, which is up in the northwest of Australia, up here. And that's biodiversity assessments where they're drilling for oil and gas, and they need to actually be assured that they're not destroying anything and so on. This is a pretty interesting one as well. This is off the Barrier Reef, and they're looking for sunken reefs which are the result of previous sudden meltings of the ice caps. All right? So it's all associated with basically predicting what's going to happen in the future. And again, they've managed to discover new reefs down there that the scientists have never been able to find before, just by doing some of these accurate surveys. And finally, this is an interesting one, doing things like cuttlefish surveying. So again, we're using a lot of machine learning ideas to take the images that you've seen before, take the vehicle, do long surveys, and effectively count flora and fauna and use that information to compute biodiversity estimates. So again, this perception issue in more complex environments, I think field robotics and other areas have made good progress in a relatively short space of time, where we can actually deal with this sort of complexity of information and use it and provide useful results for a range of different applications. So let me move on to the last bit of my talk and say something about mining. This is incidentally an iron ore mine. Goethite is why it makes it look yellow rather than black for hematite. And the mining companies have really changed their attitude, as I'll talk about in the last couple of years, in terms of the way that they view automation. For me, mine automation is basically one of the grand challenges in field robotics. It's, in fact, probably the main reason I went to Australia in the first place. It brings together all the elements I've just talked about. These are big environments, complex to automate, big systems. You might have hundreds of machines working in this sort of environment, and an interesting and varied data fusion problem in terms of how you do perception and how you fuse information, and quite clearly the size of these vehicles and the operation, a big emphasis on integrity, safety, and all these sort of drivers. So it has to be said, I think that a lot of the recent interest is actually driven by the commodities boom, but I think now there has been a seed change in the fact that people are prepared to actually look now at integrating this kind of, trying to automate this kind of environment. So I'll give you a little bit of history here too. When I first came to Australia, I think we were all interested in doing the usual field robotics thing. That is, building a robot, either a robot truck or a robot LHD. This is a project that we worked on with Peter Cork and CSIRO, and we were focused on this. And it turns out really that mining companies were not interested in this. We tried to do a lot of projects in this area, but in the end it was hard to justify the bottom line of having an automated truck or an automated loader or anything. And also it has to be said there was a lack of automation culture. No one in the mining industry really knew how to exploit automation technology. And I think we and other people turned away then from looking at just automated vehicles. And instead, we tried to understand what the mining companies were interested in. And primarily, mining companies are interested in making money. I guess that's true of any company, right? What we thought instead is we would actually develop components of an automation system that really built towards that. So looking at things like safety, predictability, and so on, rather than automating different types of vehicles. And we've done a lot of work in this area. Safety is a very big driver in the mining industry. And this is Eduardo Nabat, one of my colleagues' favourite overheads, showing you why safety is important in mining. These are very big trucks. And they often go wrong. And if you're in one of these things, and this happens on a non-zero basis, it happened last month twice in Australia, then you need to be concerned about this. So if you build automation systems that can improve safety, then that's a big selling point.